So I am glad to present one more session of the Logica Universalis webinar with the technical assistance of Anne Herbst. And today, Raja Natarajan, so we have a session with colleagues from India, and Raja Natarajan, who is member of the editorial board of Logica Universalis, will chair the session. Please, Raja.
Thank you, Johnny. Welcome to everyone for this Indian session today. We have a young speaker for today who's going to speak about Venn diagrams and boundaries. But before that, we have a presentation of the Calcutta Logic Circle from Mihir Chakraborty, who's the founder of the Calcutta Logic Circle, and he's also been mentoring it closely right from the time she started it. So first we'll have a brief presentation about the activities of the Calcutta Logic Circle, and then we'll go on with the talk and Venn diagrams. So I hand over the floor to Mihir Chakraborty, please.
Well, thank you, Raja, very much. And this is a very good evening for all of you from Kolkata, India. Thanks to Jean-Yves Pejou and the LUW team for giving me this opportunity to present Calcutta Logic Circle before this audience. It is really not a formal body, but it is continuing for about how much? About 30 years, more than 30 years now. Since time is not much, I would like to go straight to the website of Calcutta Logic Circle. So I would request Shantan to. Okay, is it visible? Can you see this slide?
Yes, it's visible.
Is that okay? Okay. Now, Calcutta Logic Circle is as I said, is an informal group. It's continuing for a long time. It originally started as a study group and gradually developed into research group in the sense that members, so-called members of this group, they do their own work, but they derive lots of inspirations and information and also training from these activities of the group. So I would request to Shantan to come to the history part of it. Shantan, can you show us the history? Yeah. There is a date here which is really not very important, 14/11/1987. Although this is a definite date, but it is a fuzzy day that way, because I don't remember some of us sat and discussed and started to run the activity of this group on and from this particular day. But I should mention, along with, I was definitely there at the beginning, but along with me, there are two other important persons. One is Professor Bhattacharjee of the Department of Philosophy, Jadavpur University, and the other, Professor Ranjan Mukhopadhyay, at that time was in Ravindra Bharati University, but later he switched to Vishwabharati. But I must mention three names. One is Professor Horogauri Narayan Gupta, who was a former student, PhD student of Alfred Tarski, and Professor Pranab Kumar Sen and Tushar Kanti Sarkar, both from the Department of Philosophy, Jadavpur University. All these three persons were very much, helpful to us, extended all sorts of help to the group. Okay, maybe we can come to the activities part. Okay, we generally run two kinds of activities. One is a weekly meeting. This we are continuing for over this 30 years. And the other is a annual meeting. So in the weekly meetings, you can see in the slides that some recent activities are shown here. For example, topology via logic, and I mean, and then its developments done by Purvita Jana, and other lectures were some other lectures were set theory of classical and non-classical. By non-classical, we meant paraconsistent, which was actually given by Saurabh Tarabdar, and so on. I would like to show you some earlier events. Can you show, Shartan, some? Yeah. This is, can it be further down, Shartan? Yeah. So here you will find, no, I mean, up. Here you will find some programs of the weekly programs. And you can see the name of Grand Prix there. He was at that time visiting, and so he gave a talk. And Moha Banerjee was there, and Ranjan Mukhopadhyay gave several talks on the topics, as you can see in the slides, and so on. And further down, Shantan. Okay, maybe further. Yeah, here you will see some earlier topics that we discussed in these weekly meetings. So you see here algebraic logic. So we discussed algebraic logic, and then first order predicate logic, and undecidability, and so on. So this kind of activity continued for over 30 years. Now, regarding the second kind of activity, that is the annual meetings. This is sometimes called, generally called annual meet of the logic, CLC. So here you can see from, the topics of the seminars or workshops from 2019, down to, back to 2001. What is that? Yeah, 1999. Okay, so 1 year, I don't see 1 year there. 1 year is missing. I don't know what happened, but you see, this kind of activity, running this kind of activity for an informal group is quite difficult. But we got help from formal institutions like Calcutta University, Jadavpur University, and others that you will get in the website. So we are lucky in that sense. Now I can show just one slide here of 2005. It is where Wilfred Hodges and Tim Poston, they were present. Can you show me? Yeah, here. This was held in Jadavpur University, and here among the speakers we had Shantal. Can you just make lower? Yeah, names here. Yeah, you see, Amita Chatterjee was there, Wilfred Hodges, Benedict Lowe, and Amita Mukherjee, IIT Kanpur, Ranjan Mukhopadhyay, and Piero Pagliani of Rome, Tim Poston, and Amit Shane. So these were, these kind of things we are going to, I just showed one of the years program of one of the years only, but you can get other programs and speakers in other slides. So, and we can now go further, go back. Yeah, further down, there are some other names who here, who very important names. We are very lucky that so many people really participated and gave talks here. So you can see Raja's name, Supratik Chakraborty, and Shankar Panavar, and so on. So there are many other names. So this is about the annual program. Now we have, besides this, we have some other programs also. Shanta, sure, yeah. So among these other programs, a very important one is that we observed 3 consecutive World Logic Days. The first one, you all know that it was initiated by Baju, and now, of course, it is UNESCO program, but Baju is behind that. So you can see here the 3 consecutive years program: 2019, 2020, and 2021. In these other programs, I should also mention that there is another. We built up another organization called Ali, Association for Logic in India, in which CLC played a very important role. Besides these activities, there were some other logic programs in Kolkata, held in Kolkata, which was not directly organized by Calcutta CLC, but CLC was very much effective there. In some of these programs, Zaib's Beju was present, and many others. I would now actually ask Shanton to show the members. Of course, there is no formal membership, so this is a very fuzzy set. This is the current members, a list of current members, and you can understand there are some people coming and going, but some keep on. That is interesting. So we can get a slice of the membership members. You can see the faces from a picture. Yeah, here is one shot, and but this is just one. We can understand. You can understand that this is just only one slice of 1 year of one particular moment. And now this will change. This changes. We don't have any register. We don't have any record of membership fees and all. So in the next picture, in the next talk, Reetu will be talking on universe without boundary. I consider our group, CLC, is a prototypical instance of that universe without boundary. Thank you very much.
Thank you, Mihir Chakraborty. So are there, so we can take, if people have any questions or comments?
Well, I would like to ask, so this CLC, Calcutta Logical Circle, it seems that it's very active. Can we say that it's the most active center of logic in India? And what are the relations between CLC and other people working logic in India?
No, I cannot claim ourselves to be most active, but it is definitely active. And in a sense, the current logic activities in India has been, in a sense, initiated from this center. Of course, there was another center, which is not a center, but a few people in Chennai, very important names, Ramanujam and Kamal. They were doing logic there, and we had interactions. We had connections, and the connection was set up much later. And through these connections, the Association for Logic in India, or ALI, was developed. So, I mean, as an answer to your question, I can say that CLC was instrumental to developing logic activities in India.
Thank you.
Okay, so we have a few minutes. We can take more questions. If anybody has any queries about the Calcutta Logic Circle or its activities, or any suggestions for them.
Yes, I would like to ask, what are the main themes, the main subjects that the Calcutta Logical Circle are concerned with? Non-classical logic, meta-logic, or everything related with logic.
Yeah, thank you very much. Shantan, can you show the first slide? First slide. Here you will see some, I mean, answers to, there will be two answers. One is that what we do in our weekly seminars. In the weekly seminars, we generally read new types of logics, or the types of logics that are not usually taught in the universities or schools. This is one. And the second thing is that members of Calcutta Logic Circle, they do their own research work independently, and you can see here some glimpses of some kind of research work that emerged from Calcutta Logic Circle. So the first one is, okay, rough set theory and its logic, that is a kind of model logic, many kinds of model logic. Here is fuzzy logic, actually fuzzy logic in the strict sense, as Peter Hayek, etc. call it. We have paraconsistent logic and paraconsistent set theory, vagueness and approximate reasoning, modal logics, non-monotonic reasoning, belief change, linear logic, and logic of diagrams. So these are some areas where members have worked and contributed.
Thank you.
Okay, if anyone else has any questions, they can either raise their hands or just speak up. Okay, so I don't see anyone.
Okay, thank you very much.
Before we close, Mihir Chakraborty, would you like to say anything more? Okay. Okay, thank you, Mihir Chakraborty. Thank you very much for this presentation of the Calcutta Logic Circle. Now we can move on to the second part of today, the talk by Reetu Bhattacharjee. Before I invite Reetu to begin her talk, let me introduce her very briefly. Reetu is going to talk today on Venn's diagram system for universe without boundary. Reetu is a young researcher. She just finished her PhD last year from Jadavpur University. She has a background in mathematics, and her PhD was in the Department of Cognitive Science. She has research interests apart from mainly diagram logic, but apart from diagram logic, she's also interested in mathematical logic, modal logic, category theory, and also logic and religion. And she has, so the talk she's going to give today, these are papers which were published in Logica Universalis. As part of her career, as part of collaborative work, she's been to Tallinn University of Technology, worked with Aarti, and she's visited the Sun Yat-sen University in China, Guangzhou, and she also has an independent collaboration going on with Anirush currently. So Reetu is interested in both classical as well as non-classical logics and how to look at them through diagrams. So welcome Reetu. Let me hand over the floor to you. Listen to your talk, please.
Thank you, Professor Rajan. Good evening, everyone. So today I'll be presenting a diagram system for universe without boundary, which is called Venn 01. It's a joint work with Professor Mihir Chakraborty and Professor Lopamudra Choudhury. Now, it is hard to say when the journey of diagrams in logical reasoning started, but its popularity rose with the notable works of Leibniz, Lambert, Euler, Venn, Peirce, Carroll's, and many more. Most of these diagrams were mainly used for syllogistic reasoning. Later, in 1896, Peirce introduced his existential graph, which can represent binary relation between any two terms. Previously, it was not possible to do so using any of the diagrammatic system that I have shown in the previous slide. Both Gardner and Randolph introduces their diagram to represent propositional logic. But Gardner introduces his network diagram just as an aid to visualize truth table problems in propositional calculus more efficiently, whereas Randolph's cross diagram were introduced to actually use diagram not only for representing truth values of complicated compound proposition, but also to reveal relevant facts about those propositions without engaging in complicated Boolean operation. But Sheen was the first one to successfully establish a logical system that is, logical systems that are based on solely diagrams. These are Venn 1 and Venn 2. And Sheen also established that both of the systems are both sound and complete. From Sheen, we can say that the era of diagram logical system has started. Today's talk presents an extension of Sheen diagrams, which was primarily done by Choudhury and Chakraborty. Choudhury and Chakraborty extended the work of Sheen and Hammer by incorporating names of individual and absence of individual. In Choudhury and Chakraborty's work, figure 1 represents that an object A is in P, and figure 2 represents that the object A is not in P. The set P is represented by the closed curve, and the universe of discourse is represented by the rectangle. In classical sense, figure 2 also can be represented by an equivalent diagram, which is figure 3. Here, this notation A bar is the absence of the individual A. But if figure 2 and figure 3 are equivalent, then why there is a need for a new notion called absence? The reasons for introducing such a notion are as follows. The cue to the notion of absence comes from the Indian logical system Naya. Like Naya thinkers, we believe that in our cognition, absence of an individual is directly perceived in a locus, just as we perceive the presence of an individual in a locus. We do not generally infer the absence of something by observing its presence somewhere else. Let me just skip this. So if we again go back to this 3 figures, we can see that figure 3 depicts the absence of the individual A in P directly, as figure 1 depicts the presence of A in P. Whereas in figure 2, we derive the information A is not in P by seeing A outside of So this information is a kind of derivative from the information depicted in figure 2. The second reason is that there are real life situations where we cognize that an individual is absent in a certain location through a mark representing the absence of that individual. An example for such a situation as provided by Chaudhuri and Chakraborty is the attendance register book of the students of a class is in 1-1 correspondence with the set of students. The representation of the absence of a student, say A, is marked by a symbol just as is done in case of the presence. Now here Chaudhuri and Chakraborty are not pointing at the aspect of administrative convenience, but rather at the cognitive impact of this practice. No mark corresponding to some student would bring to our mind the message no information. Thus, in the register, absence of a student in a class is shown by a mark and not by his or her presence somewhere else. Another reason for introducing this new notion is that cognition of the absence is that we believe cognition of the absence of an object A and the absence of another object B are different. Depiction of these absences by A bar and B bar leads toward perceiving these differences in a straightforward way. Moreover, by incorporating the notion of absence, we reduce the clutter in a diagram. Consider these two figures. Now, figure 4 and figure 5 are equivalent, but figure 4 is obviously less cluttered than figure 5. Cognitively, figure 4 represents the information that is A is not in the region A minus B minus C much more efficiently than figure 5. This clutter in a diagrams increases if more than one individual are considered. For example, these two equivalent figures. Here figure 6 and figure 7 both represent the universe, represents the information that A is not in the region common to B and C but not A, and B is not in the region A minus B minus C, and C is not in the region common to A and C but not B. But figure 6 represents this information much more efficiently than figure 7. The next reason is that the notion of absence becomes helpful for diagrammatic representation when the set P is recursively enumerable. A set P is recursively enumerable if and only if there is an algorithm which, when run to determine whether A belongs to P or not, will terminate with an answer yes if A is in P, but will continue forever if A is not in P. Now consider these figures again. If P is recursively enumerable and for any element A of the universe, if A belongs to P, like figure 1, then it would be locatable by a Turing machine. But if A doesn't belong to P, then Turing machine would no Turing machine would locate A in the complement of P. In this sense, to denote that A does not belong to P, we cannot use figure 2. We need to use figure 3. Another reason is that this notion also becomes helpful for diagrammatic representation when the name has no referent. That is, A is an empty term. Suppose A is an empty term such as Pegasus, so there is no referent. So we cannot again we cannot use figure 2 to represent A is not in P. We need figure 3. In the context of open universe, the notion of absence becomes more necessary. Becomes a necessity. Chaudhuri and Chakraborty introduced the notion of open universe. In open universe context, the universe has no boundary. For this reason, the universe is not static. It is in a flux. It is continuously changing. New object may appear and existing object may disappear. Along with standard object, unknown, fictitious and logically absurd object may also be considered to be included in this universe. This system based on open universe is called Venn. It was published in Studies in Logic in the year of 2012. Here I should mention this. Venn does not capture the dynamicity of the universe and only present static slice of it. In the case of open universe, there is no there is no absolute complementation of P. So we discard the rectangle in such a case. So if we again consider these diagrams, then the corresponding diagram for figure 1 in this scenario will be like, and the corresponding figure for figure 3 will be like this. But there is no diagram corresponding to figure 2 in this scenario, as we do not encourage the existence of an object without at least one positive ascription of property. So again, to represent that A is absent in P, we need figure 3, which even without the rectangle is meaningful. I will discuss this case in the later slides. By incorporating the notion of absence in the system, 3 interpretations have been generated. The first one is classical, which says that if absence of A is in P, if absence of A is in the set P, then A is in its complementary region, and vice versa. In the second interpretation, if absence of A is in P, then we cannot necessarily say that A is in the complementary region, but the converse holds. This interpretation can be understood from the angle of recursion theory and Turing compatibility. As I have mentioned earlier, that if P is recursively enumerable and if A doesn't belong to P, then no Turing machine would locate A in the complement of P. So we cannot have figure 2 from figure 3. However, we have taken a more general stance. From A bar or absence of A in P, there may arise 3 possibilities. One, that A exists in the complement of P and is locatable in Turing machine. A exists in the complement of P and is not locatable by a machine. A does not exist at all in the universe of discourse. The first 2 cases is the case of recursive enumerability. That is, from 2, we can say A is not necessarily locatable even if it exists. Case 3 may arise when A is an empty term. This situation is considered in free logic. In the third interpretation, properties, more specifically, positive ascription of a property plays a fundamental role. There may be properties with empty extension, but object without at least one specific object without at least one specified positive ascription of a property are not accepted here. For this reason, there is nothing corresponding to figure 2 in the system based on the third interpretation. In our understanding, the non-P region in the figure 2 represent an exclusion, not the ascription of some property. 3 formal diagrammatic systems have been established based on the 3 interpretation of absence. They are Venn, Venn-N, and Venn-O1, based on the first, second, and third interpretation of absence, respectively. Among this system, the system Venn-N may be considered as a base system, where adding the A introduction rule, we get the system Venn, and from Venn-N, by deleting the cross introduction rule, we get Venn-O1. I now show the syntax and semantics of the system Venn-O1. The primitive symbols of this system is closed curve, which represent monadic predicate. Here, the shape of the closed curve doesn't matter. It can be a circle or it can be like this. Shading represent emptiness. Cross represent non-emptiness. There are finitely many names of individuals, and their absence are denoted by a bar over them. There are finitely many names for closed curve called labels, which are denoted by capital letters. Broken line connects individuals, which represent exclusive disjunction between them. and the single line connects crosses and the wall, where this line represents the inclusive disjunction. And this sign used to join two type 1 or type 2 diagrams with the help of the inclusive disjunction sign. The type 1 and type 2 diagram will be defined in the later slides. Now, system Venn and Venn have exactly the same kinds of primitive symbols. Their differences with the system Venn is that along with these list of symbols, there is an additional symbol called rectangle, which represents the universe. Also, there is no need for this sign to connect type 1 or type 2 diagram, as the LCC or the inclusive disjunction also connect rectangle. This list of symbols, that is shading, cross, names of individual, their absence, sequence of crosses connected by inclusive disjunction, sequence of individual connected by exclusive disjunction, are all considered as diagrammatic object for all the three systems. There are three types of well-formed diagram: type 1, type 2, and type 3. This is for all the three systems. I will describe the type 1 diagram for the system Venn. In Venn, a single blank closed curve with a single label attached to it is our type 1 diagram. This single closed curve can have one or more diagrammatic object inscribed within it if it satisfies the following condition. That is, the diagrammatic object will not occur outside the closed curve. Two identical cross or a sequence will not occur in a diagram. And two singles A bar will not occur in the same minimal region. Before going further, I should explain what is minimal region. A basic region is a space enclosed by a curve or by a rectangle. Now, suppose we have these two curves, these two basic regions, then these disjunct spaces are considered as minimal region, and a region is a union of some minimal regions. So again, to be a type 1 well-formed diagram in the system Venn, if shading occurs in a minimal region, it should cover the entire minimal region. Two nodes of LCC or LCI will not occur in the same minimal region, so this cannot be happening. Again, nodes of LCC or LCI will not extend outside the collection of the closed curves. Here are some examples where the first one says that the first one represents no information. This represents that A is in A. This should be A, sorry. This represents that A is empty, A is non-empty, and A is absent in A. These three diagrams are inconsistent diagram, as this one represents that A is both empty and non-empty. This one represents that A is empty and A is in A. And this says that A is both present and absent in A. So we can have diagrams like this where it represents that A is in A, B is in A, and A is non-empty. Similarly, we have type 1 well-formed diagram for the other two systems, where the differences are that single blank closed curve should be within a rectangle to be a well-formed diagram, to be a type 1 well-formed diagram, and it can have one or more diagrammatic object inscribed within it or outside the rectangle, provided it satisfies all of this condition. Now we don't need these two conditions here. For a diagram to be well formed in these two systems, as object can occur outside of closed curves as long as it is inside the rectangle. Some examples are here. Next is type 2 well-formed diagram. A type 2 well-formed diagram is a diagram with more than one closed curve that can be ordered in a sequence C1 to Cn such that the closed curve Ci divides all the minimal regions obtained from the closed curve C1 to Ci minus 1 in exactly two minimal regions. There is exactly one minimal region which is inside Ci but outside the curve C1 to Ci minus 1. Suppose we have the closed curve C1, C2 and C3. Then the minimal region obtained from the closed curve C2 and C3 will be like this. So if we draw C1, it divides all the minimal region in exactly two parts. And there is one minimal region which is inside C1 but outside this two closed curve. After forming such a diagram, it should satisfy all of this condition. That is, minimal regions so formed may have or may not have entries of diagrammatic object. Labels should be attached to each of these closed curves and different labels for different closed curves. The closed curve should not pass through the signs cross A or A bars or labels. And the rest of the conditions are similar to that of the type 1 well-formed diagram. Here are some examples of type 2 well-formed diagram. The type 2 well-formed diagram for the other two systems is again a diagram with more than one closed curve, but within a rectangle. So again, if we have closed curve C1, C2 and C3, then the minimal region, then the minimal region formed is by these two closed curves, this and this. And if we introduce C1, as you can see, they are all divided in two parts. Again, we don't I'm sorry, just a second. Okay. I'm sorry, there must be some kind of technical difficulties. Just give me a second. Sorry for this. Here are some examples of type 2 well-formed diagrams in the system Venn I and Venn IN. Now, the type 3 well-formed diagram is formed Now, the type 3 well-formed diagram is formed by joining type 1 and type 2 well-formed diagrams with the symbol and this inclusive disjunction. Example is like this. So this says that either this diagram or this diagram or this diagram. Now, each of these single diagrams are called component of this entire type 3 diagram. For the other two systems, we don't need this sign, as we have rectangles to keep the diagram separated from each other. These signs are just used as a bracket. Example of type 3 for the other two systems are this. Now I will describe the rules of transformation for each system. Like it was mentioned before, we can take the system Venn as a base system. So I will first take the rule of the system Venn. There are 8 transformation rules. These are introduction rules for closed curve, A-bar and cross, extension rule for LCC and LCI and components of type 3 diagrams, elimination rule for all the diagrammatic object and closed curve, unification rule, rule of splitting sequence, rule of excluded middle, rule of construction, and inconsistency rule. Now to this list of rules, I add the introduction rule for A that states that let D be a type 1 or type 2 diagram such that there is no A sequence in D. Then D may be transformed into a diagram by introducing an A sequence such that each minimal region of D has a node of this A sequence. For example, as you can see, the D prime is obtained from D by introducing an A sequence such that each minimal region has a node of this A sequence. By this, we get the system Venn. The absence of the rule of introduction of A from both the system Venn and Venn represents the concept that seeing absence of A in some set P, we cannot necessarily say that A is in its complementary region. Now again, we go back to the set of rules of Venn and we delete this rule, the introduction rule for cross, which state that let D be a type 1 or type 2 diagram such that there is no cross sequence that spreads over the whole rectangle. Then D may be transformed into a diagram by introducing a cross sequence in D such that each minimal region of D has a node of this cross sequence. An example is like this. So by this we get the system Venn. This rule was in both the system Venn and Venn, as universe in both these systems are non-empty. But this cannot be said for the system Venn. So we cannot have this rule in the system. I would like to mention here that there is another cross introduction rule that is common for all the 3 systems, which state that, loosely speaking, if we see an A in some set P, then we can introduce a cross in P. Semantics. Now we define the semantics of the system. We define a model of the system Venn to be a triple CIH, where C is a non-empty collection of sets not exceeding the numbers of label of the system. However, some or all the members of C may be null set. And I is a function assigning members of C to all regions of all well-formed diagrams such that IR is equal to IS whenever R and S are counterpart region, that is region labeled by the same label. And I of R plus S is the set union of IR and IS. Similarly, dot is set in intersection and a minus is the set complement, set disjoint. And H is a partial function assigning object HA of union C to the names of individual A. Since H is a partial function, HA may not be defined for some A. Now for the system Venn, we again define a model to be a triple UIH, where U is a non-empty set and I is a function assigning subsets of U to all regions of all well-formed diagrams such that it satisfies the all 4 condition as we mentioned earlier, with an additional one that IR is equal to U whenever R is a basic region enclosed by a rectangle. Here also H is a partial function assigning object HA of U to the names of individual A. For the system Venn, we have the same triple as model, where only difference is that H is a total function. So if there is a name A in the language, then there is a corresponding object HA in U. true in a model. Suppose we have a model M, CIH, then we say that type 1 or type 2 diagram D is true in M, denoted by this notation in the system when I01, if and only if this 4 conditions are satisfied. That is, if R is shaded, then IR is null set. If R has a cross sequence, then IR is non-empty. If R has an A, then HA is an element of union C and it belongs to IR. If A bar is in R, then there are 2 conditions that either HA exists in union of C, but it doesn't belong to IR, or HA does not exist at all. If D is a type 3 diagram, then we say that a model D is true in a model M if and only if at least one of the component of this type 3 diagram is true in M. For the system when IN, the model is UIH. And again, we say that the type 1 or type 2 diagram D is true in M if it's the following condition 1 to 4. Among this, the condition 1 and 2 remains the same as the system when I01. The difference in the condition 3 is that here HA is an element of the universe U, and if A bar is in R, then HA does not exist in U, or if HA exists in U, then HA doesn't belong to IR. That is, if HA is locatable, then it belongs to its complementary region. For the system when I, true in a model is defined as same. The true in a model is defined as same as the system when IN. Only exception being in the condition 4, which in this system states that if A bar is in R, then HA doesn't belong to IR. That is, HA belongs to its complementary region. This is because as H is a total function, for every A, there exists an HA in U. For all the 3 systems, the syntactic consequence is defined as, suppose we have a non-empty finite set delta of diagrams, and a diagram D is said to be a syntactic consequence of delta. Suppose delta is a non-empty finite set of diagram, and a diagram D is said to be a syntactic consequence of delta if and only if there is a sequence of diagram D1 to Dn, where Dn is D, such that each diagram is either a member of delta or is obtainable from earlier diagrams in the sequence by one of the rules of transformation. Semantic consequences defined as that we say that D is a semantic consequence of delta if and only if D is true in every model in which every member of delta is true. Let me just skip the slides. We have already discussed this. Okay, the statement of soundness is that if D is a syntactic consequence of delta, then D is semantic consequence of delta. All the 3 systems are proven to be sound. The statement for completeness theorem is that if D is a semantic consequence of delta, then D is also a syntactic consequence of delta. All the 3 systems are also proven to be complete. This is the scheme for the completeness theorem. We have taken that for any 2 single diagrams, suppose that D prime is a semantic consequence of D, then all of these cases can occur, and each and every case in each and every cases, D prime has proven to be also a syntactic consequence of D. Here are some bibliography. Thank you.
Thank you, Reetu, for a very interesting talk. It's quite a lot of material to absorb.
Yeah.
So now the floor is open for questions. Does anybody have any comments or questions on the talk? Please, you can raise your hands or type your questions on the chat window. Okay, while people are thinking about the questions, let me ask Professor Mihir Chakraborty, would you like to add, amplify anything that Reetu said? Mihir, can you hear me?
Yeah, I'm sorry, I didn't. Yeah.
Okay, fine. So
Now I think you can.
so we are waiting for questions from
What I
others.
was going to say is this,
Yeah.
and that Reetu has definitely very nicely mentioned all the purposes of introducing this the new symbol, a bar, and this really comes from, I think she has mentioned, comes from the Indian, classical Indian knowledge system, where absence is also considered as something real. This she has mentioned. I would like to simply say that, I mean, to accept this notion becomes difficult for the, so to say, the standard minds. It becomes a bit difficult. My experience also on that, when I wanted to present this thing before, it was very difficult for the audience to really have an idea that absence is really present. So this is one comment. And the other comment is this, that we definitely developed the notion, but what Reetu has been able to do is to give a rigorous proof of the semantic, rigorous definition of the semantics and soundness and completeness of the systems. She just mentioned that in the first system, the individual cannot exist without any positive property being stated. This is one very important point from the standpoint of philosophy, that whether we can think of objects without ascribing any positive property to it. So this is a controversial issue, but the position that is taken here is that we cannot. I mean, whenever we state an object, we name an object, we automatically think of at least one positive property ascribed to it. Okay.
Thank you. We have a question on chat from Carrie Butler. I can read it out. Or Carrie, would you like to say it yourself? So Carrie wants to know, is there a representation of obscurity?
Sorry, what is the question? Is it a question?
Yeah, the question is there a representation of obscurity?
Oh, okay.
Or hidden knowledge? That's what he means by it. Reetu, would you like to say anything about this? You can look at the chat.
Yeah, I saw it. It's interesting. Okay. I actually didn't understand the question very well. I have to think about it.
My answer will be perhaps the same symbol. I mean, there can be another symbol for obscurity also. it is not absence. Okay. So if I have an obscure object, I can perhaps put another mark along with the name of the object. But I mean, naming is necessary. I mean, without whatever we are doing here is really naming the objects and predicates and then discussing their properties. So my answer, I mean, as I can, I mean, immediate, instant answer is that absence is not obscurity. Obscurity should maybe perhaps represented, but we should understand the properties of obscurity first so that they can be formalized a little bit, at least.
See, he's trying to clarify what he means by obscurity. He means hidden knowledge, things that are not known explicitly to everybody, probably.
Hidden knowledge means hidden property, is it?
He says hidden knowledge. So
are we talking of obscure objects or obscure properties?
Obscure knowledge.
So it should be clarified.
Yeah. Okay. So meanwhile, there is a question from Julio Stern. Yeah? He says, concerning the existence of absent properties, he says, can you make a connection with Meningonian logic?
Which logic?
Meningonian.
Oh.
Meningonian. Non-existent object.
Not sure. I don't know. Recently, I'm reading that. But,
does he mean to say Meinongian logic?
Meinongian, oh, Meinongian.
In that case, it speaks of some sort of subsistence. It is something different from existence, and according to Meinong, subsistent entity is another variety which is to be added to the world of existent things. So it's not the same as absence, I think.
But what about Monilpa? What is your opinion about this? About these empty terms? Are empty terms considered Meinongian also?
No, not at all. I don't think so. Because empty terms means it is absence. It speaks of the absence. And Meinong, when Meinong speaks of some other terms which is not existent, he calls it subsistent. This is a completely different term used as having the same status as the existent entities. So it is something making the world a big heavier. If I add some subsistent entities to the existent entities, then the world becomes heavier. So it's not absence. I don't think it's represented by the empty term.
Okay.
Okay, so before I read out the next question, let me invite Carrie Butler again. Can you unmute yourself and speak, Carrie?
Can you read the question?
Okay, so let's, okay, so there's another question from Budvi Cha. He says, do you think that the concept of absence has helped to give a fresh insight into mathematics and or logic, into either mathematics or logic?
Okay, who is going to answer? Reetu answering?
I didn't get the question. Sorry, my internet connection got unstable. What is?
So it's there on the chat. So let me read it out. So he says, do you think that the concept of absence has helped to give any fresh insight into mathematics or logic?
It gives a representation of absence. It was not previously done. And also with the help of this concept, we can give a diagrammatic representation for recursively enumerable set and also for empty terms. So yeah, it might be.
May I respond? Raja, can I say something in
Yeah,
this?
sure. Please go ahead.
No, first of all, in terms of logic, it is definitely giving. There is no question. No, should not be any
Sorry,
doubt.
I didn't get you. What did you say in terms of logic? It is?
It is definitely contributing.
Okay.
The notion of absence is definitely contributing in
Yeah.
case of logic.
Yeah, so probably what he wants to know are some immediate examples that could probably clear it up for him. Yeah? I mean,
Oh, example means, I mean, giving example right now
yeah.
is difficult because it is a kind of negation after all. It is
Okay.
not the classical negation.
Okay.
Absence is a kind of negation. So when I say A is absent in P or absence of A is seen in P, then I classically I can say A is not in P. But since we are not taking, I mean, these two are not equivalent, as Reetu said. So it is definitely a negation, but not the classical one. And it is not also the intuitionistic negation also. It has a flavor of intuitionistic negation, but not really it is slightly different from that. So from the standpoint of logic, it is definitely, I think, it's contributing. From the point of mathematics, I mean, very difficult to say because we don't really perhaps understand mathematics, what mathematics is. I mean, one can perhaps create a new kind of mathematics out of the notion of absence, incorporating the notion of absence. That is possible, and but not done. So this question, I think, is not, I mean, that interesting. I mean, how does it help in mathematics?
Okay.
One answer could be this from pragmatic standpoint, as Reetu has said, that you can try with the notion of absence. You can try with the notion of absence in actually solving some practical problems. That is possible, and that has been already done. So the clutter is reduced, and so you can use of mathematics sometimes, by using classical mathematics may be more cumbersome, while using absence in classical mathematics may give result more, I mean, directly. Some experimental work has been done in this regard, not by us, but others. There are certain results there. Of course, they say that it is almost equivalent. Their findings have said that these are equivalent. If somebody tries with the, I mean, with absence and without absence, their findings have, according to them, have proved, have shown that they are give equivalent conveniences, which I think should be tried again. And apparently, it seems that showing absence directly gives should give better result.
Okay.
For the I want to take this question again.
Yeah, go ahead.
I'm sorry. I made a mistake. There was another question. So carry on.
Okay. So there's somebody else who's raised his hand. There is Andres Bobenriet. Andres, would you like to? You can go ahead, ask your question.
Okay, thank you very much. I want to ask about the paraconsistent case and how this will help to deal with the paraconsistent situation, especially related with true contradictions and all the polemic about the existence or not of that kind of things. So we will have here presence and absence together in the same graph, how it will help to that, and how it will prevent explosion or from A and the absence of A to get to B and any other thing like that. That's it.
For the current scenario, this diagram, all these three system has classical explosion. That's why I said that when A is empty or non-empty, it gives us an inconsistent diagram. I don't have how to get a paraconsistent logic out at this moment, but it can be done. But like I said, I don't have any current idea now. This was also a question raised by Graham Pist, I think, for the paraconsistent logic.
Okay.
No, as I see, in that case, rules have to be changed. If you want to include paraconsistency in it, because you are able to show the contradiction, depict the contradiction, but what you have done in all the three systems, you have taken that from contradiction leads to explosion. So you have to drop that rule at least. And if you do that, and if you can prove some completeness and soundness will be there, no problem. But about completeness, you can check. But in that case, this rule has to be straightaway rejected. What is the name of the rule, Reetu?
I'm sorry if I may.
What?
The thing is that the rule that you are talking about is the inconsistency rule, that
Right.
anything follows from an inconsistent diagram. We have to bar this rule to get a paraconsistent logic.
Right. So what will happen?
Somehow, but
that rule is dropped. Will that a kind of paraconsistent, diagram logic for a kind of paraconsistent logic? Will that
if
be?
we drop this, if we stop this rule, that is, this is the classical explosion for the diagrammatic system. If we drop this rule, then we might get paraconsistent, but I still have to think about it. I currently don't have the idea how to get, what to do by barring this rule, what can be done immediately.
No, can you show us the rule? Is it possible to is it there in your slides? The
rules, yeah. The name is there, but I haven't shown the rule yet. Let me.
Okay, there is a question from Ranjit. Ranjit, would you like to speak up?
Yes, am I audible?
Yes, you are. Go ahead, please.
Okay, sorry, this is a very general kind of question. General pondering, actually, not very well framed question, I think. In quantum mechanical phenomena, some people may be knowing well. A particle's presence in a given box, let us say, or a given region, is not exactly concomitant with its absence in the complementary region. In a nutshell, roughly three kind of scenarios can happen. Like the particle is inside a box with certainty, that is probability 1. The particle is in a superposition of being in this box and not being in this box, or in a superposition of being everywhere, and the particle is absent in the box with probability 1. Now, presence with probability 1 and absence with probability 1 can be probably captured well with some kind of Venn diagrams discussed here, but superposition is the thing that is kind of problematic. Probably everybody would agree. I mean, there are two aspects of superposition, like one is constructive, another one is destructive. Under certain settings can make the detection probability in some place 1 and 0 in some other setting, etc. So considering all this, I was wondering, this could also be a motivation for developing a kind of diagrammatic logic applicable to this kind of quantum phenomena. This was, I was wondering about it in one of the physics problems that we were dealing with. It's called first passage time. The first passage time problem basically asks the following question. There is some random phenomena, like a random walker is in a room. What is the probability density in time that say this walker walks out of the room at t is equal to 5 minutes, t is equal to 10 minutes, etc., etc. So to deal with, to frame such or to translate such classical questions into quantum phenomena, at least I thought I needed some such kind of diagrammatic understanding. Now there are, yes, sorry. So there are, I know there are many attempts at giving a logical understanding of quantum mechanics, but there is also diagrammatic approaches, but to the best of what I have seen, they do not exactly talk about this kind of situation. So other kind of logics are like, probably some of you are aware of Newton da Costa's Schrodinger, so-called Schrodinger logic, or non-individualistic logic, or irreflexive logic, which simply removes one axiom, A is equal to A. So so maybe the question here can be something like, what can, in general, can some such axiomatic logic systems, let's say this irreflexive logic, be translated into a diagrammatic logic and vice versa? Or in general, what do you think of scopes for using diagrammatic logic to describe this kind of naive quantum phenomena? I'm sorry, it's a bit long and it's not exactly precisely formed question. And
thank you very much.
It's to all of the audience. There are, I mean, it's not exactly to the speaker, so anybody may try to add something to the question. Yep.
Actually, I don't know what kind. I recently saw some kind of application of Hayes diagram in quantum theory for the understanding of quantum theory. I can't remember the work actually. And for the diagram systems has been evolving every day.
Yes.
So
Yes.
there might be a possibility. There might be. We have
Okay.
to work on it.
Yeah. So, well, thank you.
No, I can mention the Feynman diagrams. I do not know whether you are aware of this work of mine.
Yes, yes, but they are not, to the best of what I know, they are not diagrams of this kind. I mean,
True. That's true.
But they are diagrams.
They are group theoretically characterized, etc., by mathematicians, and they are some kind of mathematical objects. But I don't know precisely, but my guess is they are not the kind of diagram I am trying to looking for. I'm more or less trying to draw a Venn diagram for the question of whether a quantum particle is in a given region or is not in a given region, or is in a superposition of being and not being, this kind of at best maybe this question can motivate to some novel types of diagrammatic Venn diagrammatic logic. That's all.
Thank you. This maybe can done, but I can't say that now.
Okay.
I'm not sure.
But thank you.
Okay, thank you, Ranjit. So,
Yes.
are there any more questions or comments? I see a few specialists in diagrams in the participants. Would anybody like to add to what Reetu said?
Hi, may I ask a little question?
Yes, please go ahead.
Yes. Hi, Reetu. Thank you for your very interesting presentation. I'm currently studying Indian classical logic, and so I really appreciate the reference you made on the Indian classical tradition, the reference to Anupalabdhi, Abhava, or Abhava. For some authors of Indian classical philosophy, the absence or Anupalabdhi is a valid reason, a good reason to make an inference. And I have a question about an application of your system. Do you think, you know that diagram logic, we use diagrams also to illustrate inferences? Do you know that we may use your system to illustrate the classical Indian syllogism in which Anupalabdhi or absence is a logical reason? It would be probably very interesting. You know, we have some problem in illustrating the logic of Dharmakirti, for instance, with the Venn diagrams. I wonder if your system, it would be more efficient, more productive to illustrate, to give a Darstellung of this kind of Anupalabdhi or Abhava inferences. Thank you very much.
Thank you very much. Can you give me some papers about it, since you said there are diagrammatics on Indian classical, which shows the Indian classical logic? I would like to look at them.
Lorenzo, your mic is muted.
Okay. Okay, you have to, if I understand well, you have to look at classical authors, Indian authors, to establish if your diagram, your system is not.
No. As you said, if I understand you correctly, that there has been use of diagram in Indian classical logic, right?
Yes, but only Venn diagrams.
Talking about,
yeah, by Karl Popper, for instance.
Yeah. Okay, on only Venn diagrams. I said that if you can send me the papers, if you have some papers on, then
yes,
look at it, and
I will send you
this will
a mail.
I would love to look at it.
Okay, I will send you a mail and share this paper. with you.
Thank you.
Perhaps he is saying that your diagrams will help him to represent the Nyaya theory of perceiving absence through the method of Anupalabdhi. That is he saying.
Yes, thank you very much for the interpretation, and I'm very sorry for my bad English. I'm very sorry.
May I
That's
know
not a problem.
is it whose question was this? May I know his name?
This is Lorenzo.
Lorenzo Leon.
Okay, long time.
No. Mainong's question is put by another person, another professor.
Different question.
Cla-
About Avava.
Yes, that was a different question. Clary or something. I can't remember exactly the name. CB. It was the initial CB. I don't remember
Butler, you can find it in the
Kari
chat.
Butler. Yeah.
Kari Butler.
The initial I can remember.
No, already you see the in Gunnery's work there is already a lot of diagrams used for absence. So it's a different. I mean, they want to represent the Indian system as a whole. I mean, their attempt is to represent the Indian system as the present question here has also wanted to do. But Reetu's attempt and our attempt were just to use this notion for extending Venn diagram system. So here is it is not that I mean, all aspects of Avava will be captured or has been captured by the diagram system that has been developed by our group here. But of course, it is possible. Of course, it is possible. One can definitely try to do that and see what happens and where lies the difficulties and what are the problems. That one can check only. I mean, one can check and try to modify the diagram system as well.
Okay, we are nearing 90 minutes from the time we started. We have time for one final question. Would anybody like to add something? Okay, if not, then let me thank Reetu and Mihir once again for a very nice talk. Thank you very much. And before we close the session, I hand over the floor to Johnny. If you'd like to say something about the next talk in this series or the new talks that are starting tomorrow. Johnny, please.
Okay, thank you very much. So it was thanks to everybody who take part to this meeting today. So the next session of the Logica Universalis webinar will be August 11th with a talk by Yale Wise from the City University of New York. And tomorrow we are starting a webinar on logic and religion as we talk about this here at this webinar. When there was a session with Dov Gaibai on Talmudic logic. So people who are interested, they can also show up tomorrow. It will be at 11 in the morning. We'll have a webinar every month on this topic of logic and religion, remembering that next year we will organize the third World Congress on Logic and Religion in Varanasi, India. So everybody also is welcome to take part to this event. So that's it. Thank you, Angie, for managing the organization of this one more session. And we hope to see everybody again in August.
Thank you. Thank you, Angie. Thank you very
much.
Thanks, Johnny.
Bye-bye.
Bye-bye.